Welcome to another Teacher Tobin video. We're going to be talking about hexadecimal conversions today, which is under Edexcel GCSE Computer Science, Topic 2, Data, and the reference would be 2.1.6 if you're following the videos in order. We've talked about base 2 number systems, binary, zeros and ones. We've talked about denary numbers, which is 10 values, 10 fingers, how we normally count. Yet, although computers only use zeros and ones, the hardware only presses on and offs, zeros and ones of those transistors. We, as humans, use other numbers-based systems to represent data and instructions because they often are more efficient, take up less space, and are more human readable. So before we look at hexadecimal numbers, I'm just going to quickly tell you about a number system that's used in computers called octal. Okay, now this is not in the specification for Edexcel, so don't panic and don't freak out. I'm just showing it to you for general knowledge. Oct, as in octopus, 8 values. If we've got 4, 2, and 1 for our binary values, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, what are the total patterns we could have? 2 to the power of 3 equals 8. There are 8 total patterns because it's 0 and positive number 7, positive integer 7, in total 8 combinations. How is that used? Well, in computers, they might have, especially Linux, you might have read, write, and execute permissions. Let's say you have a 111 on that file that you can read, you can write, and you can execute. You might have a read-only file, which is just like 100. That might be read-only. So octal is used, but you don't need to know that. So not in Edexcel. All right. I'm just showing it to you for general knowledge. All right, so let's look at hexadecimal, which is base 16. Hex being 6, decimal 10. That's a good way of remembering it. Now, the first values are quite easy to remember. We do 0 to 9, right? 0 to 9, just as normal. But when we get to 10, instead of saying 10, we say A, B, C, D, E, and all the way up to F. So 10 equals A, 11 equals B, 12 equals C, 13 equals D, 14 equals E, 15 equals F. All right. So this is the key difference, and it saves a lot of space, obviously on the computer. If you're representing, it's just using one character to represent multiple numbers. So let's look at the binary equivalents of these numbers because it will help us later. So F, what is F? Well, it's 8, 4, 2, and 1. So in one nibble, we would have our 8, 4, 2, and 1. We'd have all of them turned on. That's the biggest number we can have in hexadecimal in terms of one digit, that 15. So I'll write here 4 bits equals 1 nibble, and that's the biggest value that we've got there, 8, 4, 2, and 1. So what's E? Well, it's the same as that, except we don't have the 1. What's 13? Well, it's 12 plus a 1, 8, 4, and 1. What's 12? It's just 8 and 4. 11 is 8, 2, and 1. And 10 is 8, and 2, and 0. So those are the binary equivalents there, which will help you. And you could also go through 0, 0, 0, 0, up to this for 9 in binary as well. So let's have that as a little sort of cheat sheet that we can go back to and refer to. You could even write that on your exam, might be helpful, just so if you get a question on hexadecimal, that you'll be able to go back and forth with the values. So let's work through some examples. I will first provide some binary numbers, base 2 numbers, and we'll work out how to do them in hexadecimal. All right, there we go. So this is the key to doing this. This is how you're going to do it. I think this is the easiest way. You look at the binary number and you split it up into nibbles. Split them up into nibbles. So, and then you look at each one in terms of 8, 4, 2, 1. 8, 4, 2, 1. All right. And you're going to do that for all of them. We're just going to sort of speed run this. 8, 4, 2, 1. 8, 4, 2, 1. So you split them up into nibbles. So we had an original binary 8-bit number, 1 byte, and we split it up into 2 to make 2 nibbles. And then look at them in turn. So we've got 0, 1, 1, 0. What's that? It's a 6. And 6 is just the same in hexadecimal than it is in other number systems. Here we've got 8, 2, and 1, so that's 11. And 11 is B. So if we put these together again, that's going to be 6B. So 6B is our way of saying that that base 2 number in base 16 is equivalent to 6B. Then you could also work it out. Once you've got something in binary, it's pretty easy to go to denary, because you just look at the total thing. 128, 64, 32, 16, 8, 4, 2, and 1. So that's 64 plus 32, which is 96, plus 8, which is 104, plus 2, 106, 107, I believe. So there we go. That's the denary value for it. That's the denary value. 107 base 2 value and base 16. So let's do the next one. 0, 0, 0, 0. Well, that's just going to be 0. 1, 0, 0, 1 is 9. So 0, 9. So you just put them together, 0, 9, that's the base 16 value. And that's just the same as it would be in denary. Here, we've got them all turned on. That's 15, that's 15 if we're looking at just the nibbles, you see. And what's 15? It's F. So F, F. You know, put them together, FF is that, the equivalent of that in base 16. And you'll probably recognize that from Photoshop or web design when you have hash or octothorpe, as they call it, FF, 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 which stands for red, green, and blue, RGB, so it means 255, 255, 255. The maximum value of red, maximum value of green, maximum value of blue is white. So that's what white would be for your screen or your projector or TV, something like that. So it's much easier to represent white as 6 characters rather than 1111, 1111, and it's more human readable as well. Okay, so let's now go to sort of the opposite way. Let's have some hex numbers that we want to convert into binary and denary. Why not? Okay, so 48. 4, 8. That's the base 16. Do the same thing. It's split them up into nibbles. Split them into nibbles and then look at each one. So 8, 4, 2, 1. 8, 4, 2, 1. 8, 4, 2, 1. 8, 4, 2, 1. 8, 4, 2, 1. 8, 4, 2, 1. And so what's 4? 0, 1, 0, 0. That's 8, 1, 0, 0, 0. And then you can combine them back into one long binary number, which should be 64 plus 8, which would be our 72. So in base 2, 0, 1, 0, 0, 1, 0, 0, 0. And in decimal, it's 72. Okay, so we're just doing it all different ways because you never know quite what the exam is going to ask you to convert from or to. 6a, let's have a look at that. So how do you do 6? Don't need an 8, got 4, 2, don't need a 1. A is 10, isn't it? Let's go back to our chart. So we've got 8 and a 2. So combine them all together. That's our base 2 number, that's our binary number. And if we want to get the equivalent denary number, we just total up the value. So 64, 32, 2 and an 8. All right, so 32 plus 8 is 40, 104, 106. All right, 106 in denary. Here we go, F9. Well, F is the biggest number we can have in hexadecimal, so that's got to be 15. 8, 4, 2 and 1 is 15. 9 is 8 plus 1. So again, combine them all together. Sorry, that was a little bit crude. Let me draw that nicely. So that's the binary number. So the way I would do this is all of these together is going to be 255 and then minus 2 and 4. So 255 minus 4 minus 2 equals 249 and base 10. Because once we've combined them back together again, we're looking at 128, 64, 32, 16, 16, 8, and a 1, and a 4 and 2, but we don't have those 4 and 2 in there. That's the technique. That's how I would do it. That's the easiest way of doing it. You can also see the first 16 to the power of 0 is 1. 16 to the power of 1 is 16, and I think 16 to the power of 2 is 256. You can do it to the powers of. It's possible to times them, but I find that method to be a little bit slower, more cumbersome, harder to remember. So I would just stick with the nibbles method. I think that's going to be better for you. So let's have a look at this question, exam style question. Computer game designer creates a new game. Colours in the game are represented in hexadecimal. Okay, so we looked at that idea earlier, didn't we? Convert the binary numbers in this table to hexadecimal. So how are we going to do that? Well, they've kind of given you a clue because they've given you a little gap between the nibbles. So you just look at each nibble. 8421, 8421, 1101, 1110. 8, 4 and 2 is 14, which would be E, the equivalent E in hexadecimal. Let me just write it there so we're not encroaching on the space. 8, 4 and 1 is 13. So DE is what I make it. And then here 8 and 2 is 10, so that's an A. and 1111 as an F. Here we've got 8 and a 4, sorry, 8 and a 4, which is 12, and our 12 is C. And then we've got a 4, which is just a 4. You just have to split them up and work out each nibble. So that's our 3 marks. That's not too bad. Convert the hexadecimal number. Okay, so we've got to convert hex number. That's not the number 12. So be careful there. That is not the number 12. What it is 12 in the base 16. So how would we do this? In binary, we'll just take that 12, we split it up, 8421, 8421, and 1 is just 0001 in there, and then 0010. Okay, and then combine them together. That's worth a 2, 4, 8, 16. So 16 plus 2 equals 18. So that's the denary. There you go. If you can get it to binary, then you're pretty much good to go for any conversions after that. So hopefully that all helped you. If it didn't, let me know. If it did, let me know. If you want me to do more on that, also let me know. And I'll look forward to seeing you in the next video.